All right, now we'll come to we're getting to the meat of the chapter. So what we're going to do is, now we're going to, by the way, the mass of an atom is, so let's put this in perspective. So most of your masses are about 60 kgs, 60 to 100 kgs. Okay, so the masses are 60 to 100 kg. The mass of one hydrogen atom is, so the mass of a hydrogen atom is 1.6 times 10 to the minus 27 kg. Okay, so if you take a nitrogen molecule, it's 30 times that, so it's about 50 into 10 to the minus 27 kg. Okay, so an air molecule is very, very tiny. Okay. And now what we're going to do is we're going to relate the properties of the atoms and molecules to macroscopic variables such as pressure, volume, and temperature. And we are studying an ideal gas, meaning we are neglecting the interactions between them, interactions between the molecules. There's no molecular forces between them. Intermolecular forces, they only interact when they collide and so on. And all these collisions are elastic and all that kind of stuff. Okay. So we're considering a large number of molecules now, but the density is low enough where the average separation is large compared to the size of their molecules. Okay, so this would be, this is, so again, the separation between molecules is large compared to their sizes. Okay, so that's what and they obey Newton's law, and they move in all directions with equal probability, and they undergo elastic collisions among themselves and with the walls, and the forces between molecules are negligible. Okay. So now the pressure, so here's the deal. Here are these tiny molecules, they're bouncing off the walls, and that's how they're exerting this pressure on the wall. And this pressure on these walls is 60 atmospheres. 60 atmospheres is, so 1 atmosphere is 15 pounds per square inch. Okay, so 60 atmospheres would be 60 times that, 90 pounds per inch square. Okay, so roughly, so this gas, these tiny molecules, by bouncing off the walls, are exerting a force equal to the weight of a person on every inch square of the walls. Okay, so that's pretty amazing. And the way they exert force on the wall is when they bounce off, the wall exerts a force on them to make them bounce off, and the reaction force, so for every action there's an equal and opposite reaction. So the gas molecules are exerting a force on the wall in that direction. Okay, the wall exerted a force in this direction to make them bounce off. Okay, and so oops. So when a gas molecule bounces off, the wall exerts a force on the molecule in this direction, and the molecule exerts an equal and opposite force on the wall in that direction. Okay. So the force that the wall exerts, so what this is showing you is, here's this molecule. There's the velocity, here's the x component of the velocity, y component of the velocity. And you see the y component of the velocity does not change, only the x component changes. The wall always exerts a force perpendicular to the molecule, and that's the force that the wall exerts on the molecule. And you can go through the derivation. So the force that the wall exerts is that, and so the gas is exerting an equal and opposite force on the wall. Okay. And so we know the directions of the force, and so the pressure So if you take the magnitude, and this is just summing over all the molecules, you have n molecules in the gas, and d is the dimension of the box, d is the dimension of the box. Okay. So if you go through all that derivation, the pressure is the force that the gas exerts divided by the area of the walls. Okay. And you go through all this, the pressure of the gas works out to be 2/3 N over V. N is the number of gas molecules, V is the volume of the chamber. So this is the number density. This is the number density of the gas molecules times the average kinetic energy per molecule. So this is a tiny, tiny microscopic quantity, and this is being related to a macroscopic quantity. See, pressure is something that you measure using a handheld instrument, and you've never seen a molecule. So here you're relating the pressure, which is a macroscopic quantity, to a microscopic quantity. So this is the first big time expression that you've seen. Okay. So pressure is related to this microscopic quantity. Okay. And now let's, so there's the expression again. Pressure is number density times the average kinetic energy of a molecule. So let's let's go to that simulation. And so what we'll do is, it turns out that the average kinetic energy, so let me write this expression down. So pressure was 2/3 mv times 1/2 mv squared. Again, this is the average kinetic energy per molecule. And in a second, you'll see that this is related to the temperature. Okay. So we'll keep the temperature constant. And what we saw in that expression was, what you saw in this expression was, so we're going to keep the temperature constant, meaning we're going to keep the average kinetic energy constant. So to increase pressure, if you increase the number of gas molecules in the same volume, the pressure should increase. Okay. And you'll see that. Okay. So what we'll do is we'll fill this thing with more molecules. So as you add more molecules, the pressure went up. You see that? And that's what this expression is saying. So the pressure is related to the number density and the average kinetic energy. You can increase the pressure by either pumping more molecules in or making them go faster. Okay. All right, so here's the ideal gas law. In this expression, you bring volume over there. Pressure times volume is 2/3 N times average kinetic energy. So PV is 2/3 N times average kinetic energy. Here's the ideal gas law. If you compare the two, what you find is 1/2 mv squared is equal to 3 kg, 3/2 kg. Okay, so the average kinetic energy is related to the temperature. You double the temperature, you double the average kinetic energy of the molecules. Okay. Also, so the temperature, so in a gas with a mixture of, in a gas with a mixture of molecules, see there, both the gases are at the same temperature. So their kinetic energy is the same. So if a molecule is heavier, it's moving slower than a lighter molecule. Okay? Since their kinetic energy is the same. So let me, so 1/2, a heavier molecule will move slower and a lighter molecule will move faster. Okay. All right. Now, here's another important fact about this, which is the equipartition of energy. So you saw that the average you saw that the average kinetic energy of a molecule is 3½ kT. Okay. Now, a given molecule, uh, it doesn't care which way it's moving. So it'll move equally, it has equal freedom to move in all directions. So now this is 1/2 m average Vx squared plus Vy squared plus Vz squared. And this is 3 times 1/2 kT. Okay. So since um, each there's no preferred direction, you would think that the energy in the x direction will equal the energy in the y direction would equal the energy in the z direction. So what we're saying is the average energy along each degree of freedom is equal to 1/2 kT. Okay, and this is the equipartition of energy. Okay, so there's 3 terms and 3 times 1/2 kT. Okay, so what we're saying is if you have a thermodynamic system, and what is a thermodynamic system? A thermodynamic system is a system that has a large number of particles. Okay, and so in equilibrium, you can associate a quantity called temperature. And what this temperature tells you is, it tells you that each degree of freedom, so each degree of freedom contributes 1/2 kT energy towards the system. Okay, so energy toward the system. Okay. So what that means is, let's say you have a thermodynamic system with n number of particles. The energy of this system is n times f, the number of degrees of freedom for each particle, times 1/2 kT. 1/2 kT is the number of energy contributed by each degree of freedom. Okay, so it's n f by 2 kT. Okay, so it's, well, actually it's divided like this, n f by 2 kT. Okay. So that's how you calculate, that's the total energy of the system. Very simple. Okay. So the equipartition of energy says each degree of freedom contributes 1/2 kT towards the energy of the system. Okay. So so there's a lot of so from this you can come to conclude a very important relationship. So the average kinetic energy is given by 3/2 kT. Okay. So we define, from this expression, we define various quantities, various speeds. So one of the things we define is the root mean square speed, roughly the average speed. So here's the average kinetic energy is equal to that. Root mean square speed is root mean square speed. So we'll come to the molecular distribution in a second, and I'll show you how to calculate this. But so root mean square speed is given by 3 kb Boltzmann's constant times temperature divided by the mass of a single molecule, or you can express it in terms of the gas constant, where capital M is the molar mass, the mass of 1 mole of that substance. Okay, so the VRMS speed is given by that. Okay, and so again, here's the equipartition of energy. Here's the kinetic energy per molecule. And V square can be written as Vx square plus Vy square plus Vz square. And this is the average kinetic energy in the x direction, average kinetic energy in the y direction, and z direction. And since there is no preferred direction, each direction will contribute 1/2 kT. Okay. The kinetic energy along each each degree of freedom or each direction is 1/2 kT. Okay. So the theorem of equipartition states that each degree of freedom on the average contributes 1/2 kT to the energy of a system. Okay, so very important relationship in thermodynamics. So if you have a monoatomic gas like all the ideal gases, like the noble gases, they're all monoatomic. So for monoatomic gases, so for okay, so for monoatomic gases, all they can do is have translational degrees of freedom along x, y, z axes. Now, if you have a diatomic molecule, you'll see this. Well, the diatomic molecule has 3 degrees of translational freedom, but a diatomic molecule can also rotate, spin, and so on. Okay, so it'll have more degrees of freedom. But a monoatomic gas will only have 3 degrees of freedom. And so the kinetic energy of a monoatomic gas is the energy of a monoatomic gas is just the number of molecules times that, which is 3/2 nkt. Okay. So now we'll talk about mean free paths. Okay, so the question is, by the way, so we did mention this, but this is roughly the average speed. So at 20 degrees Celsius, which is the room temperature, at room temperature, again, air is mostly nitrogen. Well, it's nitrogen and oxygen. So the average speed of nitrogen molecules is 511 meters per second, so 0.5 kilometers per second. And the average speed of oxygen molecule is slightly less because oxygen molecules are heavier than nitrogen molecules. Okay. But anyway, so that's the speed, about 0.5 kilometer a second. So now the question is, let's say you go to a room and spritz some perfume at one end. It will take a while for the perfume to get to the other end of the room. So the question is, if each perfume molecule were traveling roughly at 500 meters per second, why does it take so long? And you probably have guessed the answer, because a molecule just doesn't go there straight. It's colliding billions of times before it gets there. And so the mean free path is the average distance the molecule travels between collisions. Okay, so that's the mean free path. And the mean free path is given by this. Okay, so it depends on d, the diameter of the molecule, okay, which we assume is quite small, but nevertheless it's not 0. Okay, so it depends on the diameter of the molecule and the number density of the molecules. So how many molecules there are per volume. Okay, so, and this formula makes sense. The larger the molecules, smaller the mean free path. The larger the molecules, it won't go that far before colliding with something. And the greater the number of molecules, the smaller the mean free path. Okay. F, the frequency just tells you how many times it will collide per second. Okay. And that depends on the speed, which depends on the temperature and the number of molecules. Okay. So here are some typical numbers. So this is the size of a molecule. So this is about 20 nanometers, 0.2 nanometers. So the size of a molecule, roughly 0.2 nanometer. D is the distance between the molecules, average distance between molecules. And you can see that the distance is about 15 times that of the size of the molecule. All right, so so the distance between molecules is roughly 15 times their size. The mean free path is 100 times the distance between the molecules. Okay, so what we're saying is, so let me go to the chalkboard. If the molecules are this big, they're about that far apart, and they will go so if the molecules are this far apart, they'll go, well, a lot further than the end of the iPad before they collide. Okay, so that's what this mean free path is. The mean free path is 100 times the average distance between the molecules. So if this were the average distance, they would go almost to the end of the screen before they collide. And the frequency of collisions, so these air molecules are colliding about 1 billion times a second, 2 billion times a second. Okay. So that's what's happening. All right. The molecular speeds. So you so you saw that in this gas, not all molecules are moving at the same speed. So here's a plot of the speed versus the number of molecules. So this formula is telling you this many molecules are moving at that speed and so on. Okay. And this is the Maxwell-Boltzmann's distribution. And that's what's given by this formula. So the probability that a molecule is going at that speed is given by this formula, 4 pi times m, or 2 kt to the power kt to the power 3 halves, v square e to the power of minus mv square by 2 divided by kt. Okay. So now let me just point out one important thing about this formula. So the probability, that a molecule will have speed v is proportional to, so we'll say constant times 3 halves, proportional to the temperature to the power of 3 halves, v square speed square e to the power of minus 1 half mv square divided by kt. And you see this term is the kinetic energy. Okay, so it's c 1 t to the power 3 halves v square e to the power of kinetic energy divided by kt. So the higher the kinetic energy for a given temperature, lower the probability that the molecule will be going at that speed. Okay. Anyway, so there's this distribution, and so here's the distribution shown for 2 different temperatures. So here's the distribution for 900 degree Kelvin, and this is the distribution for 300 degree Kelvin. So when you heat a gas, what happens is this curve flattens. There are more and more molecules moving faster and faster, and so on. Okay. So as you heat the gas further and further, the curve will flatten and move to the right. Okay. Well, this end is anchored, but this end will move to the right. Okay, so the curve will get flattened. All right, this is called the Maxwell-Boltzmann's distribution. And if you wanted to know the number of molecules with a given speed, you just multiply that by the total number of molecules you have, and that'll give you the number of molecules moving at a given speed. Okay, you can go to that simulation as well. Okay, here, let's go to that simulation. Okay, so here's the Maxwell-Boltzmann distribution. So what this is telling you is, so you have 100,000 molecules, and I believe these are hydrogen molecules. So at 800 meters per second, there's 2,251 molecules going at 800 meters per second. there's 540 molecules at traveling at 1,000 meters per second, and there's 60 molecules traveling at 1,200 meters per second. This is the most probable speed. This is the average speed, and this is the RMS speed. Okay, so you can see that the RMS speed is greater than the average speed, which is greater than the most probable speed. But anyway, they're quite close to each other, and anyway, so we roughly talk of them as roughly the same. Okay, so here they're given, so they differ by about 20%. So VRMS speed is 516 meters per second. Average speed is that 476 and 422. Okay, so this is the Maxwell-Boltzmann distribution, and you see as I increase the temperature of the gas, the curve flattens and moves to the right. Okay. So that's the molecular speed distribution. Okay, and now, so this is important. Now, what we're so let's say you have a glass of water in a room, and if it's not 100% humidity, if it's 100% humidity, what happens is there's water in the atmosphere. The number of molecules coming in are equal to the number of molecules going out, escaping from the glass. So the number of molecules coming in from the air and merging with the glass water in the glass, and the number of molecules escaping are the same. Now, if it's less than 100% humidity, then what that means is there are more molecules escaping than coming in. Okay, so and when the molecules escape, it's the fast molecules in that distribution. It's these guys that are escaping from the glass. Okay. Also, another important example is at the center of the sun. You know that 4 protons are combining, producing a helium nucleus and plus energy, because the helium nucleus weighs less than these guys, you're getting energy. Okay, and at the center of the sun, even at 15 million degree Kelvin, only the fastest protons are fusing, combining. Okay, so that's what we're saying here. Inside the sun, protons in the tail have enough velocity to overcome the repulsive Coulomb force to undergo fusion. Only these guys, these protons, are able to undergo fusion. Again, of course, for the proton gas, the temp at the center of the sun, the temperature is 16 million degree Kelvin. All right, so here's how you would calculate the average velocity, average speed if you wanted. Speed times the probability distribution of speed, and integrate over dV. So let's you learn this in statistics. So if PV is the probability distribution, PV is the probability that the molecule will have speed V between V and VdV. Okay, so if you wanted to calculate average V to the power n, here's how you calculate this. PV dV and goes to 0 to infinity. So that's how you would calculate any average. So V square would be PV. And again, you'll learn all this in your probability class. Okay. So the average velocity is given by that, and it's 8 kT by pi m and so on. So VRMS speed is that, and the most probable speed is given by that. So VRMS speed is greater than the mean speed, which is greater than the most probable speed. Okay, now we'll talk about specific heats. But before I do that, let me pause and give you guys a chance to ask questions.